last class I discussed with you, in the last class actually I discussed with you about the iron carbide phase diagram and iron graphite phase diagram. So, let us move on before actually we discuss about the family of cast iron. What is the actual effect of silicon? I have been telling you that we need silicon in cast iron to promote the formation of graphite. Silicon actually reduces the nucleation potential of graphite formation. What does that mean? If you want to nucleate something from a liquid or solid, you have the phase which is to be formed, or the product phase, it needs to cross a nucleation barrier, and this barrier is mainly because of the interfacial energies between the two phases. Suppose if I want to form graphite from the liquid, the interfacial energy between the liquid and the graphite, that dictates the barrier, height of the barrier actually. Just like a bump on the road, if you want to cross a bump, you have to push it, give a little bit more energy, same thing happens for the nucleation of graphite. Now, silicon reduces that height. So, that means what? Silicon helps in nucleating graphite very easily, that is the idea. So, now that is what is said, eutectic of graphite occurs at 54 degrees Celsius temperature as compared to eutectic reaction happening at eutectic reaction for the other thing happening at 1147 degrees Celsius temperature, and this eutectic reaction is written here. The carbon concentration 4.3 or 4.26, it is better to write 4.26 because that is what is so. Okay, 4.26% carbon going to gamma of 2.14, these are wrong actually, I am correcting it, and graphite. The eutectic graphite reaction is competing, this reaction is basically competes with the eutectic reaction of Fe3C at 1140 degrees Celsius temperature. What is that? That is basically this gamma plus Fe3C. These two reactions are competing each other. In cast iron, that is what I written here, a silicon is used to control the formation of graphite phase. I told you just now, few minutes back. The eutectic reaction does not occur at 1144, nor 1148, nor 4.33% because of addition of silicon. Okay. It will actually eutectic reaction leads to formation of graphite. So, if you want to have nucleate graphite, you need silicon, that is what I have been telling you long. Okay, now, to explain that, I am showing you something new which you have not seen or probably not in the books. It is better to plot a phase diagram which is called pseudo-ternary phase diagram. Anyway, we will discuss ternary, but pseudo-ternary, which is again temperature versus composition axis, not there is no third axis, but only two axis and a 2-dimensional plot, iron with 2% silicon and carbon concentration varies, correct, because that is what happened, 2% silicon is invariably present in cast iron. So, what you see here is this is the gamma plus liquid, liquid plus graphite, gamma plus graphite eutectic reaction here, and this is the alpha plus gamma plus graphite, this is the eutectoid reaction here you see. So, everything gets modified, even this point which is normally 0.02% of carbon is about 0.05% carbon, correct, and this is what is your alpha plus graphite. This is not your perlite, alpha plus cementite, this is alpha plus graphite, and I will show you what will happen if you have alpha plus ferrite. It is not a perlite, it does not give you perlitic luster of perlite. So, now, so you can see here this has been calculated and also experimentally verified. This diagram tells you if you have silicon and then carbon concentration increases in these alloys, the phase formation will happen like this way. So, you do not see any depth of cementite in this diagram. What you see here, everywhere cementite is replaced by graphite. So, in a nutshell, silicon can be converted, because that was silicon 2% carbon with silicon, sorry, iron 2% silicon with carbon phase diagram is a pseudo-binary phase diagram. Pseudo means why? So, why pseudo? Because there are 3 components, iron, silicon, carbon, but we are plotting like a 2-dimensional plot in a binary phase diagram. That is why it is called pseudo-binary phase diagram. So, this is so therefore, what we do? We just convert silicon to equivalent of carbon, and the desired total carbon content is about, so that 4.3. How it is done? Well, as you know, silicon has a stronger effect on graphite formation. So, therefore, carbon equivalent is nothing but percentage carbon plus silicon divided by 3. So, if you want to form eutectic mixture, you must have 4.3% carbon. So, I can actually, if I have a cast iron with certain amount of carbon, I can decide what is the amount of silicon required, so that I can get into 4.3% carbon. That is what I want you to take a message out of this. So, that is what is known as carbon. This is equation is taken from the range of carbon, silicon, ferrous alloys for different types of cast iron. Okay, this is valid for almost all the cast iron. Similarly, phosphorus also has effect, which we normally ignore. Phosphorus actually is a more important element, I know, very interesting element in cast iron. And so, you know, phosphorus is added to cast iron many times to formation of graphite. So, again, if you have phosphorus, we can also have a carbon equivalent. Carbon equivalent is but carbon percentage plus silicon plus phosphorus divided by 3. You see the equation very clearly. So, basically, if you have a cast iron with silicon and phosphorus and carbon, and you want to have a 4.3% carbon equivalent carbon, then this is the formula you have to use to determine basically silicon and phosphorus content you need to have to get 4.3 ballpark figure. Okay. So, that is the effect of silicon, that is the quantification of silicon. Okay, I have discussed for the last 5-10 minutes, last class and this class. Now, let us discuss about different cast irons. You know, as you know, cast irons I have described here 5 types. First one I have discussed is grey iron or grey cast iron, where carbon is present as a graphite, but flex. Okay. Then you have a white cast iron, where carbon is present in carbides, they are often alloyed. Third one is known as, this is the second one is white iron. Why it is called white we will clear when I discuss about white iron. And third one is a ductile iron, in which you have again cast graphite as a second phase, not carbide, and graphite as a shape of nodule or spheroid. Fourth one is the malleable iron, malleable cast iron. You know, is basically a cast iron in which you have a carbon present as a tempered graphite. And the fifth one is basically alloy, if you have alloying elements, and then this will happen. Okay. So, now let us first discuss about white iron. We will spend little bit of time white iron, but most of the time we will spend on graphite, the grey iron and spiral graphite iron and malleable iron. White iron, you have, these are the features. You have mostly less than 1% silicon, 1% silicon. It is brittle and hard, very brittle due to presence of this cementite, not used for any application except to make malleable iron. This is a source material for malleable iron, you have to understand that. So, what is it? Because it contains primary cementite, that is why if you break it, these are the primary cementite, white things you see here, these are the white things cementites. So, this was gamma earlier and this was cementite, which is the eutectic reaction product if you have less silicon into the alloy, and this gamma later on transform into perlite, obviously, because gamma is not stable at room temperature. That is what you see perlite in each of these grains. Here again same thing, these are the cementite, this is the perlite, you cannot see inside because it is etched heavily. This was not etched heavily, that is why you see even the perlite lamellae inside it. Because it contains cementite, so if you break it, it is brittle, the surface looks like white, that is why it is called white iron. That is the main reason why you call a white iron. And because it is brittle, it is not used for any applications whatsoever, except for making malleable iron. Now, you know, white iron can be both, it is a eutectic alloy, 4.26% or 4.3% carbon. So, you can have hypoeutectic or hypereutectic. But if you have a hypoeutectic, what will happen? You have a hypoeutectic alloy will have primary gamma, obviously. Let me go back to the phase diagram. Yes, if you have a hypoeutectic alloy here, so you will have primary gamma forming. Please go back to my eutectic phase diagram discussions. From this temperature you will have form primary gamma, and then finally eutectic reaction will happen lead to formation of cementite and gamma. So, as you see here, so these are the primary gamma black regions. Why? Very simple, they are the dendrites, they are formed like gamma forms the dendrites from the liquid, and they have become black. Why? Because gamma is transformed into perlite, and the moment it transforms into perlite, if you etch it, it will look like black, because internal lamellar spacing is so fine, and if you etch it heavily, they look like black. Whereas these are the regions of eutectic transformation. As you see here, the white things are cementite and black things are or gamma, okay, and that gamma again has transformed into perlite. So therefore you have two types of gamma. This is the primary gamma, which has formed directly from the liquid before the eutectic reaction happens, and this gamma is basically, this is called eutectic gamma. It has transformed into perlite again. This is also transformed into perlite again. This is what you see here. So either way you form perlite, either it is from perlite, and this perlite is basically forming because of solid state transformations, and that is why you see them black. So this is called hypo. What will happen to hyper? Yes, you have understood correctly. Hyper you will have primary cementite, see blobs of cementite, primary cementites, grains. Hyper is on the other side, right side of the eutectic. So primary cementite plus eutectic, and eutectic is this cementite plus gamma, and gamma is again transformed into perlite, because gamma is not stable. This is very important. I go back again. For hypoeutectic alloys, what you have? For hypoeutectic alloys, you have primary gamma plus eutectic gamma plus cementite. You have no primary cementite. So this is not so brittle, in fact, because it has primary gamma. Gamma is more ductile than that. But on the other hand, if you have a hypereutectic, then you have primary cementite, and these primary cementites are blocks of cementites, like you see white areas, and they are very brittle. So that is why they are never used. Even for malleable iron also we use the other one, the hypo. Okay, that is about the white iron. Therefore white iron is nothing but the steel is the cast iron where there is no graphite. Please understand that you have only cementite as a phase. So now the second one, which is very important and widely used cast iron variety, is known as grey iron. For the all the lectures for the next 10-15 minutes, I am going to discuss only on grey iron. Grey iron is basically basically cast iron family. It contains about 1.5 to 2% silicon and about 3.5 to 4.3% carbon. Where graphite is present, you do not have cementite, and graphite presents as a flex. Flex means needles, just like and remember in aluminum silicon I have discussed, silicon comes as a fiber. So needles are actually like fiber only, but little thicker. They are actually needles. They are actually better to call them as a flex. You have seen flex, like take a tree leaves, it looks like a fleck. So what you have is superimposed on it. Basically, they are actually superimposed. They can be kiss or normal type, which we will discuss later, and they can be random or preferred orientations. You see here some of them are preferred. These are preferred, okay, but these are random, long needle like. These are preferred, these are random. Okay. Matrix can be both paralytic or ferrite. So that depends upon what is the carbon concentration you have taken initially. Very simple. Okay. So suppose if I have a eutectic reaction taking place, so liquid going to gamma plus graphite, and if I keep it at high temperature, high means above the eutectic transformation temperature, above A1 temperature for a long time. So what will happen? Graphite flakes will grow, they will become thicker and thicker, and if they grow, they will take all the carbon out from the gamma. So gamma will be depleted of carbon. So if gamma has very low carbon, less than or 0.05% carbon, it will transform into alpha. It will not transform into perlite, because to you want to perform perlite, you need to have a carbon concentration more than this much, right? You see, you have remembered that curve. This is 0.05, this is 0.08. So you need more than this amount of carbon. That is what is required, correct? So therefore, you can create either ferritic matrix or perlitic matrix depending on your requirement. On the other hand, you have flex, and this flex of cast iron I have shown you nicely here. You see here some of them very sharp, some of them like wandering in the land, some of you may be doing moving around. So, they are actually long moving direction, they are not preferred oriented. And this is here you have paralytic matrix, you see that is why you see a contrast here, this is because paralyte is present. Well, we all know, we all been taught, you have also been taught, graphite looks like a flake, but you know graphite does not grow like a flake, graphite rather grows like a cabbage. Basically graphite goes like a needle, it is like this, it is like a needle. Now, if I take a cross section, I cut it off, I see like this structure, I see plex, that is what I see. So, therefore, it is like a cabbage like a structure, you see here it has started going like this, then it has gone like this, like that, you can draw. Now, when you cut a sample, you see what is a 2-dimensional section, and this 2-dimensional section will have this kind of things, flex. So, they are not like a flex, they are actually like a structure I shown you just now. And many times you will see this is what is shown here, this is actually EBSD diagram, electron basket diffraction. As see graphites, they are having same orientations, these ones, white ones, the grey ones are different orientations, that is because they are growing in a different fiber. And if you etch it nicely, you can see even graphite fibers meandering around in the matrix, that is what is shown, and meandering around the matrix. So, basically it will be much clearer when I discuss spiral graphite. So, what it basically means that graphite forms like a needle, it is hexagonal crystal structure. So, it is easy for it to grow like a needle, going along the vertical 0001 directions, okay. And that is what is required, that is what is seen in the actual microstructure. So, there are different morphologies also possible, that is what I have shown you. This is what is, let us start with this is what is small and oriented, sorry, small and random. This is what is known as rosette, it is like a rose, a rosette. This is random but associated, this is rosette but very preferred, and this is preferred. So, there are different flex morphology possible. These are all there in ASTM standard. ASTM is what? American Society for Testing of Materials. So, this standard is there. So, depending on these morphologies, you can have different mechanical properties, that is why. As you understand, graphite grows like a short fiber, long fiber, paper oriented, or this thing, there are different morphologies. This again I show. So, this is what I show A, okay. A is uniform flex, random orientation, that is what the first thing I showed. B1 is rosette, they form by inoculation, which we will discuss later. C is what? This is non-uniform flex, random orientation, non-uniform flex. They are not uniform. Uniform means thickness are somewhat bigger, somewhat bigger. And you can also have secondary graphite formation, it can be interdenitic or paper orientation, so random orientation possible. See, D is interdenitic graphite. Interdenitic graphite means the last liquid which is present in the interregion is transformed into graphite, but these three are the most important, correct. Then there are different sizes of graphite flakes. Rapid solidification results in finer graphite flakes, but if you repeat too rapidly, you will have cementites. That is because you can bypass this eutectic reaction. Unless there is a very high silicon and carbon concentrations, graphite flakes are classified by this. See, if it is longest flex is more than 4, they are actually 100 nanometers, then it is called number 1. If longest flex means these are actually numbers 50 to 100 nanometers, okay. And then you have a longest flex 20 to 50, there are 3 different types, all are long only, but the sizes are different, category is number 1 to number 6, but these are all you need to remember, depending on sizes. Okay, you see here, this is the flex number 1, very long, little long, then rosette small, and this is fine. So, flex size 6 is finer, size 1 is longer, size 2 is thicker, and size 2, 3 is also thicker, but little less longer than the size 1. These are actually for you to know, because if you want to create shapes and sizes or you want to characterize them after cinema exercise, these are what you should understand. How does it solidify? Well, very simple. First, normally what happens, all these gray irons are hypoeutectic alloys. That means they have composition less than the eutectic composition, less than 4.3 or 4.26% carbon. 4.26 is better. That is what happens when graphite is in equilibrium with iron. So, you have gamma forming first from the liquid, that is what is shown here, gamma dendrites in the liquid, and then at the eutectic transformation temperature you have, see here, okay, this is for the gray, this is for white. So, gray then you have this gamma plus graphite as a eutectic formation, these dendrites are still there, and finally you have this gamma transforming into pearlites. So, basically this gamma which is present, I showed you in the case of white iron, will also be transformed into pearlite. For this white iron, you have gamma first forming from the liquid, but eutectic reaction is different. Eutectic reaction is leading to formation of gamma plus cementite, and then finally this gamma both in eutectic and in the dendrite transform into pearlite. That is what happens solidification wise if you compare grey iron and white iron. A grey iron eutectic reaction is different. So, I think I should stop here, and just before I stop, I like to tell you grey iron is very important material. Why? Because it is widely used in the automobile. Your engine block is made of grey iron, but you know grey iron is used in the engine block not only because it contains graphite, but it is very easy to cast. Because of presence of graphite, flowability is very high, so you easily cast in different shapes. That is why the engine block, I do not know whether you have seen it or not, very complex shapes can be easily cast using grey iron. Not only that, because you have graphite as a needle present in this in the cast iron, so what will happen? Graphite will has a very high thermal conductivity, so needles will allow transfer of heat, because in an engine block you burn fuel, you generate a lot of heat, that heat needs to be conducted away. So, presence of graphite actually allows you to take the heat conducted away. So, graphite flakes, because of directionality, it can allow the transport of heat very fast. That is why you want these graphite flakes to be present in the engine blocks, and they have a very high castability, very easy to cast. That is why they are used. These are all the plus points, very important plus points of the grey iron. That is why grey iron is made of, grey iron is to make the gearbox, even grey iron is used to make engine blocks, gearbox, many other blocks, the housings in the automobiles. But problem is what? Because graphite is present as a flake, and flake has a tip, like any other thing. It's a flake means it's a needle, and at the end of the needle you have a very fine tip. So, now if you apply stress during service, there will be application of stress, and because of the stress, because a load, not stress, application of load, and because of the fineness of the tip, what will happen? The tip is fine, so therefore there will be what? There will be a lot of stress generated because of the fine tip. Area is very small, so stress is nothing but load divided by area. Because of high stress, the cracks forms there and it breaks. So, this is the problem. One of the problem, the important problem of grey iron, and that actually creates, you cannot use in many structural application where the stress is quite high. Engine is not the case, so therefore you can apply. But many other parts, stress is very high where these flakes can create problem. So, that is why we need to modify the morphology of the flakes, and that is what is done in case of nodular iron. You make them nodules, which we will discuss in the next class. Okay.